the isochron dating. This is a response to T-Rock and standing for truth. And I'm not an expert on this topic, but I'm seeing the video that I'm responding to, and I think I can give my 2 cents on the topic. So let's start. Let's see what T-Rock has to say about it. I start to say that I will talk about only a portion of the video. It's relevant to the presentation of T-Rock. It's not because there is something that I cannot answer to in the other parts of the video, but this is the presentation, so it's the most relevant part. So let's start. Okay.
Looks good.
All right, let me put this in read mode. All right, so we are defending Genesis. Genesis, of course, is an accurate eyewitness written history of the world, and what we expect to find in scientific studies of the age of the Earth that exclude biblical studies are just difficult to navigate in a scientific context, and I think that's exactly what we're going to see. I'm going to start by reviewing some preliminary methods, not Isochron, and somewhat chronologically in terms of how much time can be quote unquote measured by each method, and then I'll build up to Isochron dating. So
Okay. So as you can see, T-Rock will start talking about this kind of methods, and of course I will say a things or two. Of course I disagree about what he is saying, but let's see what his arguments are.
the question is reliability of Isochron dating. Can we count on it? And no, it's actually the problems, just like pretty much all the other dating. So,
We are going to have T-Rock
and somewhat chronological in terms of how much, and somewhat chronologically in terms of how much time can be quote.
Action.
Sorry about that.
Build up to Isochron dating. So the question is reliability of Isochron dating. Can we count on it? And I am saying no. It's actually fraught with problems, just like pretty much all the other dating methods. So an overview of dating methods: carbon-14, very popular method. It's used for more short-term kind of dates, roughly from 500 to 50,000 years old. You might hear people say up to 100,000 years. That's the theoretical limit based on sensitivity of a mass spectrometer and whether it can count that few atoms in the sample. 50,000 is typically the accept limit.
As for now, I can say nothing. Everything is fine.
10 half-lives. It's most reliable from the 500 years mentioned earlier to about 3,000 years. Beyond that, it frequently has to get cross-checked by other methods, such as varves, oxidation, cross-checked against known archaeology. And that's kind of an important idea, because essentially what you're doing is you're verifying a dating method, a chemical dating method, with an eyewitness account. And so it's also worth noting that the eyewitness accounts are used to basically fix positions on a written such as coal. There's that, no matter what date you rejected, because theoretical world for carbon-14, in 1 million years, if the planet were made entirely of carbon-14, planet Earth was entirely carbon-14, 1 million years would be enough time to it. So the most sensitive equipment imaginable should not be able to detect a single carbon-14 atom in anything 1 million years old or older. So, of course, I'm not going to go into detail here because this is just an overview, but coal does have carbon-14 in it. Dino soft tissue does have carbon-14 in it. Oil has it. Amber has it. And I didn't list it here, but diamonds have it. Of those examples, I explain easy, that sort of thing. Some contaminant.
Sorry. With these things, I have a problem because he is saying that someone is using carbon-14 to date bones of dinosaurs, and it's quite not credible. Dinosaurs are too old to be dated with this method, so I really want to know who is doing that, searching carbon-14 in dinosaurs. So I would really love a source. But as we will see later, I do not think that we will have one. So yeah.
Chronology overlap, and that overlap can happen in a couple different ways. One of them is you got two different trees, example, with enough rings present, and the strata literally overlap each other. One will be deeper than the other, so you count down to one and then kind of jump into the other one. The other way that the overlap is done is you count the rings of the first one, then you use some biomaterial in the proximity of that or that first tree, and often it's a living tree that's started with, but it doesn't have to be. But anyway, use some biomaterial and carbon date it, and then oddly enough, use a linear extrapolation to jump to another sample that's supposedly older than the first tree rings that were counted, and so they can be added together that way. So typically,
here we are talking about dendrochronology, and I completely disagree over his points, and I can tell you why. When we are talking about this kind of method, so we are talking about dendrochronology, it's not that simple. Dendrochronology is a very complex science, so it's not like we are just guessing. T-Rock is just saying, okay, it's impossible to know. Maybe there are more rings over a year and things like that. The fact is, we know when that's the case. You need to study a lot to do this kind of analysis, and we scientists can tell the difference between a ring, an annual ring, and a double ring. It's not that easy. It's not like you can just look at one cut tree and tell his age just like that. Of course, it's way more complex than that. So go figure. It's not that easy. It's a complex science, and I do not think that T-Rock either he doesn't know enough or is wrong, because dendrochronology is quite a good method, especially if you use other methods to confirm it. And I will never be tired about telling things like that. So okay. The next one are barbs. Okay. I think.
because the boulders.
Let's start again. Okay. So
Stuff has no writings with it. It's also to try and use those as some kind of anchor points for calibrating. Donnie, I'm going to stop real quick. Is my audio still good?
Yes, it's coming in real good.
Okay, thank you. That's at least one. Year.
okay. So we are at the next method, and I do not have much to say about this one. Actually, I think that it's like carbon dating. It's not like you can date the age of the Earth with this method. And T-Rock knows it. The dates are up to 20,000 years. It's too. It's a little bit too few years for these kind of things. So I think it's not relevant to the discussion because the Earth is much, much older. Of course, he thinks the Earth is just 6,000 years old, but yeah, I do not think it's a credible statement. Sorry, T-Rock. So yeah, these kind of methods, it's not relevant to the discussion of dating the Earth. And I have nothing more to say. So it's not true, for what I can tell, that it is used for millions and millions of years, and T-Rock is saying that. So yeah, I think that's not accurate at all. Let's skip this. Okay. And we are getting to the good stuff. Okay.
Stable daughter isotope, such as lead, uranium, lead.
Okay.
These amounts can be converted to H by the standard equation. NT equals NO times E to the negative KT, where N sub T is basically the amount of parent, or the amount of the radioactive element that you have now, and N sub O is the original amount that you started with. Honestly, though, this equation is missing an extension. You can build this equation out if you wanted to, because this standard equation always assumes that there's no daughter isotope present in the original sample, so there's no term included on here for it, which is an unwarranted assumption, because there's no way to know that, and perhaps taking radiometric samples of rocks of known age as a reference point to evaluate them from. It would be called a control group in a proper scientific study. We go around and gather rocks from across the globe, or whatever area you choose to study. And basically be a control group before you go trying to apply the method to formations of rocks of unknown age, so to speak, such as submarine volcanic formations that nobody's in history could have possibly witnessed. As far as I know, that practice is not actually done because it won't yield the results that deep time advocates expect to see. So, uranium lead is used for dates greater than 100 million years. Argon, for example, is used for dates less than 100 million years. That not only giving two samples to the problem here is all of this kind of ideology where you have to already know roughly the age of the sample before you can even pick it up. So that's kind of a major red flag. If you already have to know the age of it.
So here I can see a lot of things, actually. First of all, as you can see, he is wrong about a couple of things. First of all, the rocks used for this kind of analysis are closed system. They are not isolated ones, of course, but closed, yes, they are. Any open system would falsify the result of the experiment, so material cannot go in and out. If something like that happen, you can tell, because in isochron dating, you can actually tell when you have a contamination, because you will not have a straight line. Uh, I have used this kind of graph before, so I know when you got something wrong, you can tell that there is something wrong. Also, the whole thing about assumption, the Earth is old because we think it's old. Of course, it's not accurate at all. There are examples of samples that were believed to be older or younger, and the scientists did that, get that. Of course, when you have strange data sets, that means that you are wrong about something. So you can start from there. And yeah, basically, it's all that. It's not circular. You're not thinking in circles, as T-Rock is saying. It's not like that. We use those kind of things to calibrate the dates, but we know when something is wrong, and things like that happen. So we know that the method is working.
System rock formation. Here, many radioactive isotopes are water soluble. Uranium, for example, is both water soluble. So, in an open system, this creates huge problems because water or water in some form, steam, is a real common ejection from volcanoes, for example. And so with all this steam and water percolating through the mantle, you start out with a problem with most radioactive isotopes, because you're already rearranging the chemistry during the formation process. So also many radioactive isotopes readily form pores with other minerals. Uranium is notorious, of course, for forming several pores that has to be refined. So it's very difficult to say that these open systems have not been drastically affected, especially over the geological time. Okay, now that brings us to isochrons. So introduction to isochrons. Isochron dating. This measures the amount of radioactive parent isotope its daughter decay. And a stable isochron.
Of course, for the most part, this part is fine. It's not like is telling something wrong. It's quite accurate on this kind of things. Problems start after this. What I can say about the presentation of T-Rock, and I suggest you to look at the video, is that yes, his view, from my point of view, is wrong. And I will tell you a little bit about this later.
And so this is kind of what they look like whenever they're plotted. This is from the Brahma amphibolites.
Those are quite important, and I will tell you why quite soon.
And so sample part A there shows rubidium strontium system, and you can kind of see how these points plot out here to form what looks like a line. You might take note here, it says isochron plots for the Brahma amphibolites. The crosses and ellipses are the data points, sample analyses, and their sizes are proportional to the plus or minus analytical errors. Okay. The analytical
First of all, we are talking about deviation standards, and I'm quite skeptical about these graphs, and I will tell you why a little bit later. What you need to know that those in particular seem quite huge dealing standards for this dataset. And oh, hello there, Titan. Nice to see you. I'm trying to respond to T-Rock. I'm in a pretty important part because those datasets, first of all, it's not like I found anywhere the dataset, and I think it's quite suspicious. T-Rock is playing like those are data from scientists and of course are from creationists. So it's a little bit sketchy. I would love to look at those datasets, but let's T-Rock speak for himself. Let me know if everything is working fine.
literally just how accurate you think you counted the isotopes. So we also have chart B is samarium neodymium, chart C is lead. Just three different systems. Now, this particular example is showing one of the many problems with isochron dating. It was actually supposed to be a solution to single isotope methods. So I'm backing up a bit.
It's not a solution. It's a different method. Pretty important to say that. It's not like it's a solution. No. That's just creationist misunderstanding this kind of things.
The known problems with single isotope methods were what I stated is that it was too easy to account for isotopes drifting in and out of the system because they're not closed. And so essentially over the history of Raymond.
Okay. Raising the volume. Okay.
Metric dating,
Now,
what many scientists discovered was that they could always date.
now it's better. Okay.
They were given from the samples. So they sought another method in isochron plots. But as it turns out, the isochron method has pretty much all the same problems that the other single isotope methods have. But it's going to have another unique problem that is quite different and doesn't help at all. But either way, basically, when you look at isochron plots, you come to the same types of problems. You get dates that just don't make sense. And so this is one example here. This is showing an isochron age for the lights, or it shows 1.24 billion years.
Yes, it's correct. They are showing different ages, but I'm skeptical about this. Why? Because when I look at the deviation standard, I cannot believe that this deviation standard is so little. Uh, if I'm looking there, that's a pretty awful set of data. So I cannot believe that this line is accurate at all. And here I cannot tell. Uh, they seem there is a pretty much huge deviation standard too here. So I think that those two are very bad set of data, and that's maybe a little bit more accurate, and that's why you get different ages, because this line is not accurate at all. T-Rock will talk about the R square, and I think that this R square for this line is completely off. So, and I think also this line a little bit less, but that's not a good set of data at all. Absolutely not. And of course, I've tried to find those kind of data set, and I think I found nothing. I will show you a little bit later, but yeah, they are nowhere to be found.
The samarium neodymium of the same sample gives 1.655 billion years, and then the lead-lead isochron system for the same sample gives 1.88 billion years. So you might note that the plus or minus values on each one of those is well between the ages that are given by each method. So this is not a case where the error bars overlap in some way to try and give some kind of concordance between the methods. 3 different isochron plots just register incorrect dates. So if you're a geochronologist or a geologist, which date do you think is right? It becomes super subjective at that point. So something else I also want to point out here, actual plot to really kind of be, as in an actual spreadsheet plot, so that you can kind of zoom in on these numbers, because it's not totally obvious right here. But if you look at the x-axis across these, it goes from 0 to 2.0 on this rubidium strontium, and it goes from 0.69 to 0.74 on the y-axis. So what you're seeing, though, is those plots are actually very, very close together. Now, mathematically, and I will concede,
Close. I see a pretty huge distance. That's a huge deviation standard in my book. I do not see there a good set of data, so I completely disagree with T-Rock. I would love to see the data set, but I did not find it. He will give his source later. Spoiler is from creation.com. So strange, really strange that he's choosing a set of data that has a huge bias in his favor. Really, really strange.
mathematically, it doesn't technically matter, but it is a really small area that you're looking at trying to find a best fit line for. And I think the biggest problem for me, like I said, mathematically that should not technically matter, but the problem is that there are so few samples that are used for a given analysis that it's hard to have any real confidence. There is
few samples. If you are dating rocks, I think that you can find a lot of samples on a particular strata. It's not like you are working with a very few samples. And I've read the article on over creation.com, and they are saying, yeah, we are picking up 20 samples or so. They are much more than scientists use to give their analysis, and I think it's completely wrong. Let's say that for what I can tell from my experience in any lab, scientists do a lot of experiments. They take a lot of samples, and before you are certain of something, you need to have a lot of data.
this, I think, called a confidence interval with statistical analysis on things like this. And that confidence interval is, there's basically a formula for calculating what that confidence level should be. Notwithstanding, it's still a very subjective idea on how confident you can be whenever your sample sizes are actually quite small.
It's not. If you we are talking about maths, and you can be pretty sure when you have a good confidence, you will have a good data set, basically. Of course, something can go wrong with your data, but if your data is good, you can be pretty much certain about these kind of things. The R square, it's math. It's not like it's an opinion. It does not work like that. I can tell that not very good set of data, because with this huge deviation standard, the lines here, they are huge. How many lines you can fit between those lines? A lot. And that's how you know that that's not good. The equation for get the R square, it's basically how many lines you can fit here. You need to measure the distance about of these lines, and you will get a value of accuracy of this line. With this deviation standard, you will not get a good R square. You will not at all.
Considered large, I get that. But if you know a little bit about statistics, these are typically done with something like 10 crystals, zircon crystals, to count the isotopes.
Now, that's important because I read the original paper. So, yeah, he's taking that from the paper, basically word for word. Strange. Very strange.
But these particular samples, I think we'll find later, I'm not going to say here, but these particular samples actually use almost double, triple what typical samples use. So that they use a higher count, which is also a little bit odd here to get such different results across 3 different isochron systems. So what I'm suggesting is increase the number of zircon samples that are analyzed, and the plot may become quite fuzzy if you get enough of them, and you couldn't plot a I'm going to come back to another.
Yeah, because scientists they are using very few samples. What's the source for this? The paper over creation.com. I was around a lab and I never seen something like I use 10 samples, and that's good. When you want to know something, you need to send uh, samples to more labs because when you want to do data treatment right, you need a lot of data, and human error is a part of it. You need to have multiple squads working over your samples because you can tell when something is wrong if you do something a lot of times. If you are doing it 10 times, you will get, sorry, basically nothing. With only 10 samples, depends. What are those samples? You are meaning that you will do just 10 analysis or not. I think that 10 are few in any case, especially if you are working with rocks, because I would want to have multiple labs and multiple squads on my data. I would love to have multiple sources and do data treatment afterwards. I think that 10 samples, it's sketchy. Maybe I'm wrong. I'm not a geologist, but usually you need much more when you do something. And you need to repeat the experiment a lot of times before you have any confidence in it, in the results.
Idea, but we're going to come back to this in just a minute. I'm going to continue on for a second so I can kind of explain what they're trying to do here. The y-intercept is greater than 0 in an isochron plot. As you can see here, each one of these starts out somewhere above the 0 line.
Okay, fine.
The y-intercept represents t equals 0 for sample. That means, going back here, I don't know if everybody can see my mouse or not, but that point right there represents t equals 0. Okay, the linear relationship between ratios of stable isotope and daughter isotope and the parent daughter isotope demonstrates an isochron. That's a linear relationship. Nonlinear relationship demonstrates migration of isotopes or other contamination and invalidates the isochron.
Right. So you can tell when you have a contamination. He was telling me before that those rocks are open system. No, if you have an open system, you will have something that's not aligned. So you can tell that something is wrong.
So if you can't get a line out of it, and actually what they're doing, I don't have the information here in front of me, but what they're doing to do a best fit line, if you open up an Excel spreadsheet and kind of plot some stuff out that looks like it's in linear fashion, you can tell Excel to plot this line for you, and it will typically give you what's called an R-square value, and that kind of tells you how close the data points fall on the line itself. So,
And that's not close at all. So I would love to see the R square on that line because it's not reported there. Strange. Really, really strange.
like, what's real common is an R-square of above 0.95 is considered good, and if it gets very far below that, it's considered bad. So
On my experience, the line it was pointing to 0.8, more or less that. I do not think you can get more than that. I can be shown wrong, but I did not see the dataset, so I cannot tell what's the R square. I would love to have the dataset, so I will be able to um, work out the numbers and tell what's the R square. Mm, looking at it just like that, below 0.9.5, sorry, 0.95, far less. I will say it's 0.8, no more than that.
An isochron just won't be valid if that R squared number gets too low. Okay, and because it will indicate it's a non-linear relationship. The entire isochron
Non-linear relationships, meaning two, that's not a line. So that's something wrong in your data, because if you are expecting a linear relationship and you get something that's not linear, you have a problem, of course.
Now, this is not true for all systems, but most of them do follow this. The entire isochron line rotates counterclockwise as theoretical age increases. So what is the slope of the line is going to increase going uphill counterclockwise as the theoretical age gets larger. Okay, it's commonly uses 6 to 8 crystals per sample, but may use more, which is precisely what happened in these samples, as they were in the range of 7.
I would love to have a source, because it did not present one. I looked into the data here, and that's a paper from Creationist. And sorry, I would love to know more. Maybe I'm wrong. I'm not a geologist. Maybe they use very small sample sizes, but it seems really, really unlikely, unless those samples are very large, so you can do a lot of experiments with it. But to have a good data set, I would think that you need to repeat experiments for several tens of times. I think you need at least 3, 4 labs working on it, maybe with different squads, if you want to have a good data set. You cannot just drop 10 rocks on some lab and expecting a good result. You can get human error, maybe some instruments are broken, or they do not work fine. You can have a lot of problems, and that's why if you want to have a good data set, you need to send your sample to more labs.
17 to 20, I think, to do these dates. Okay, where and why it's used. It's used on igneous and metamorphic rocks that come from sources whose origin is not known from historical accounts, such as Grand Canyon, marine volcanoes, etc. This is a red flag. It can't be used on anything in known history because it's
No, you need some kind of samples, and if you are trying to measure very, very huge time gaps, will not make sense to use on everything this kind of methods. So yeah, I completely disagree with T-Rock on that.
going to yield a false isochron. It's going to render a bad date if you're able to plot an isochron, an actual linear isochron at all. You're already to to try it on. but nevertheless, it does eliminate some of the assumptions associated with single radioisotope methods, such as potassium argon that assumes all argon escaped prior to solidification, or other types that assume there was no daughter isotope present when the rock formed. The uranium lead system that I mentioned earlier is one of those. You basically in the single isotope system, like I said, you do have to worry about migration of both the lead and the uranium in and out of the system because they are water soluble and they do form compounds with and ores with other elements. So that's why this system was developed to get rid of those assumptions. It's alleged to provide 2 clots running.
So I'll talk a little bit about this slide. I think that there is much wrong with it. There is no red flag at all. You are using the right method for the right sample. It's not like you can date a chicken bone with this kind of method. It would be impossible to do so. And those assumptions, you can tell when there is a contamination because the data set will not be aligned, so you will be able to tell. It's not like you can just guess. That sample, I think it was contaminated in some kind of way. I do not know how and why, but just looking at the line, I can tell, actually. And yeah, it's not like, I think most of this slide is simply wrong. And the last point is buffering. I cannot understand it. Why you should talk about C14 methods in isochron dating? It's not like they are even in the same ballpark. Yes, they are used for more ancient dating because C14 cannot be used for those. It's a given. So let's go over this slide. Okay.
Imagine if you had a rubidium strontium isochron plot that gave you a date of 20 billion years. It's hypothetically possible to find such a thing, but no geologists accept that date because it's older than the universe. So what assumptions are involved in?
It's not like it will be not accepted because it will be older than the universe. I would love to see something like that, like isochron dating something older than the universe itself. It will be, well, of course, you will be thinking that's wrong, and I will agree with you, and I will assume that's some sort of contamination, and I will check for that. It's not like if something does not fit my narrative, it's wrong. Science do not work like that. You need to show why you are right and the data is wrong, basically.
Isochron date. Okay, no parent or daughter isotopes have migrated into or out of the samples. Now, when you look at this slide here, what you're seeing in blue is they're the ideas that I'm actually not going to contest. The red is what I will be contesting. So I'm not contesting the first bullet point there. No daughter, no parent or daughter isotope or concept.
So, as I said, you can tell when something is contaminated. T-Rock is just arguing for this. So, yeah, we can tell. It's not like we are just guessing. Not at all.
The rate of decay has always been constant. I'm not really arguing against it for or against that either. You can say the rate of decay has always been constant, and I'm not even going to invoke accelerated decay as a starting point either. So I'm basically giving that as a valid assumption. Here's the problem I have. 100% of the daughter product was derived through standard radioactive decay processes. This is a problem for a couple obvious reasons. Number one, it is an open system that you're investigating, and it is supposedly.
No, it's not. Show me why that should be an open system. Rocks are not like open. Some, they can be open system. You can have cracks. You can have ways to have gas and things like that fleeing the rock. But usually, when you are dating things like crystals or some kind of rocks, you know that rock is a closed system. It's not like those systems are simply open, and some can be open. Maybe you have some cracks, some inclusions, maybe you have some sort of contamination, but how can you tell that everything about those rocks? All those rocks are open systems. Rocks are not usually open system. It's not like you can have a gas exchange or things like that.
Millions, sometimes billions of years old, and so you have to ask yourself, how in the world did you not end up with migration into or out of this open system? Okay, and then the other assumption is that you started with homogeneous parent stable daughter isotope. It's kind of irrelevant. We'll see why here. I'm not contesting that point. Okay. Assumptions challenged. 100% of the daughter product was derived through standard radioactive decay processes. This is naive. The very processes that created primordial, pick your radioisotope, uranium, rubidium, potassium, samarium, etc., likely also created its daughter product at the same time. Even in the secular view, that's almost certainly.
How can you tell that? Yeah, we have the daughter isotope in the same sample because it was created that way. Even in a secular point of view, I cannot understand this point. Maybe T-Rock will clarify for me.
They got to be true. No event has happened in the millions or billions of years the sample supposedly existed that would have obscured the dating results. That's another basic assumption. This is also that no volcanoes in recorded history have a proper isochron signature. So how does a volcano inherit a true isochron profile if none of the young ones start out that way? It's just special pleading. Okay, and then another assumption is started with homogeneous parent stable daughter isotope. This is also irrelevant, even if it's true, because you still don't know what the starting point, how the sample originally came to be that way to begin with.
I would love to know what does mean T-Rock with Isochron signature. You cannot measure isochron dating on a new volcano. Is what is meaning. If someone has an idea about that, maybe put that in some comments below my video. And also, if someone has something to say, just say it. I'm here for that.
Okay. So we've kind of talked about some of these issues, but I'm going to go over them again. Open systems, you have a problem with ore texture, mineral chemistry, supergene alteration through oxidation, parent daughter disequilibrium through chemical or radioactive means, groundwater and soil chemistry, so pH, EH, salinity, absorption, that sort of thing. You can find this stuff at creation.com, the failure of the uranium.
Wow, that's part of his sources, and it's shocking that's from a creationist perspective. And spoiler, it's his only source. Yes, you can have these kind of problems on rocks, but you cannot simply tell that that kind of problem is for every rock you are looking at. Some have these kind of problems, and usually you can tell when you have those kind of problems.
Thorium lead dating at Kungara, Australia. And then, of course, it's what I've been arguing all along, the original, the origin of daughter elements. And I've got to here in just a second kind of demonstrate what the problem is with primordial isotopes. Okay, so there's a plethora of foreboding.
Maya, so nice to see you. How are you? Everything is fine. It's so nice to see you on a stream of mine. I'm at the beginning of my adventure on YouTube, but it's a pleasure to see you. So yeah, nice to see you, Maya. It's wonderful to see you there. Anything, if you want to say something, I will try to respond to you, and to Uranus too, of course. And it's a pleasure. Still alive. Yes, I'm too alive, actually, as you can see. And I changed my. I have a new flat, as you can see. I hope you love it. It's very comfy, and I want to stream a little bit more. Yeah, don't worry about it. I will not put your comment on screen, but do not worry. The Italian right, it's not that bad. Italy, it's a strange place. People talk much, but do not do so much. Let's say that. For what I can tell, everything is fine. Our republic is built to prevent things like that from happening. We are quite good at it, Maya. So I'm not really worried about the situation. Of course, I did not vote for that party at all, even though I want to vote for right, but in Italy it's basically impossible to do so. There is no decent party to vote in the right side of the parliament. But yeah, do not worry about it. Everything is fine. Italy, it's a place built to avoid things like that. So thanks, Maya. It's very sweet of you to be worried about me, but do not worry. Everything is fine, really. Let's continue with the T-Rock. It's almost over. I think that we have we have 10 minutes or so of content from T-Rock.
In terms associated with Isochron plots from the open literature. These are mainstream and what happened is that there's apparently quite false isochron, mantle isochron, secondary isochron, mixing line or mixing isochron, an erupted isochron, an inherited isochron, or a source isochron. And you can find this under, for those in the audience that might be interested in going to.
So that's quite important. These sources are just one sources, creation.com. I've looked into it. They have other sources listed, and that's true. But when you are talking about data, no. The data is from just creationists. And I think that I'm skeptical about it. And I did explain why. I think that the deviation standard from those graphs are quite concerning. I want to be honest.
But they will point you to source. I get that.
For what I can tell, no, they are not. I did not find the data set. Maybe I'm wrong. If T-Rock want to say something, maybe he can show me where is the data. Anything, he can do it. I'm open to be proven wrong.
The origin of parallel is not zero. They're just method. There's nothing new about finding anomalies for any given dating method. Isochron certainly is not outside of that. So, for example, strontium-84, strontium-86 compared to strontium-88 and strontium-86 in the Murchison meteorite. You can see that here in this article titled Contra or rubidium strontium dating. Basically, some of these are actually stable isotopes, but it alludes to a problem called fractionation with radio or with isotopes of certain elements. Actually, many elements have a somewhat there's a process called fractionation. It refers to basically the separating of isotopes of the same element in a sample, and so there are ways that happens naturally in the Earth that basically disrupts the whole point is here that when you face examples of fractionation, it disrupts with the isotopic ratios from standard radiometric decay.
And of course, all of that is coming from just one source. And I'm pretty skeptical about these kind of things. You can wonder why.
So fractionation is just a process that distorts how you interpret those ratios to even get an isochron plot. Okay, so this is somewhat of a joke, but it's actually this is kind of the heart of the problem with isochron dating, and that is that isochron plots can be generated from just about any mixture if it's homogeneous. Random numeric simulations, physical models of mixed substances. Homogeneous state can simply be the result of physical mixing. See the slide for isochron terms, and that's exactly this bullet point number 6 exactly makes that point. It is literally called in the open literature a mixing line or a mixing ice.
It's not simple because we are talking about very, very huge numbers. The rule of great numbers. It's not like we did not test these kind of things, and we are just guessing. So yeah.
Because this is true. I've actually done this myself. I put this second bullet point on here because I went through an Excel exercise where I basically used some random number generation. And all you need, because isochron dating requires three components, the parent, the daughter, and then the stable isotope of the daughter. So in a random numeric simulation, you basically just kind of replicate that idea with, say, for example, three number ranges that are kind of, that don't overlap. They're kind of distant from each other in some way that you can put them back together as ratios, just like isochron is done. So the M&Ms, for example, you need three different colors of M&Ms. You would need a rather large bowl, granted, for M&Ms because the M&Ms themselves are pretty big. To get any kind of a decent linear plot out of that, you need a pretty big bowl with a lot of M&Ms in it. But 3 colors is all you need to match the 3 components of a standard isochron. Probably better is doing something like this cinnamon sugar example. It's a trick question. If you put a cup of...
You know what's different in isochron dating? We are talking about numbers that are a little bit higher. So when you get to a precise ratio, and you can get it from more samples than one, I will say that's quite improbable. That's just something that you get because you are lucky. Just to give a reminder, we are talking about just for a mole of compound, about numbers up to 23 zeros, if I remember correctly, with the Avogadro numbers. So yeah, it's not like you can just pick up a ball of material and say, yeah, that's a good model for what I'm talking about. I think it's not.
Cinnamon into 3. Well, sugar, depending on the sample size you take. If you mix it partially, you might get what looks like an isochron in some places, but in other places inside that same bowl, you would not get a linear, quote-unquote, isochron plot. But if you thoroughly mix the bowl so that it is obviously fully homogenized, you're going to get exactly what you put into it in your isochron plot. You're going to get 1 part cinnamon and 3 parts sugar, period. And I mean, that example only has 2 components, but add a 3rd component. And when you break the ratios out, just like isochron plots are done, you're going to get the same thing. You're going to pull, per the standard method, 6, 8, 10, 15, 20 samples. It doesn't matter. Count the colors of each one, and then make your numeric ratios and plot them out, and you will get an isochron plot out of powdered sugar and cinnamon and perhaps one other ingredient that's easily identifiable. But the point is that isochrons literally are just mixes. That's all they are. There's no way to demonstrate anything else but that they are mixes. So I would encourage.
Except we usually know the starting condition for the formation of a certain crystal or things like that. We know that are closed system and not open ones, as T-ROX is telling us. So we know that those ratios are made by those processes and anything else. If you have contamination, you will be able to tell because you will not get a line, you will get something else. So it's not like that. Not exactly. Let's say that.
Actually try this. You can remix it up, you know what you're going to get out of it. If you don't know what you put into it, you can make the plot, and then once you get done with the plot, you'll know exactly what you did put into it. because the ratios are going to come out if it's thoroughly mixed exactly how you put them in there. So there are a plethora of bad examples that can be investigated here: concordant, isochronic, cardenous basalt, and associated.
Just look at those examples. I can see a plot here. Creation.com, Sterling. I remember something about Snelling. Maybe he's a creationist. Just kidding. He is a creationist. Creation.com and creation.com. So there is a plethora of examples coming from just one source. When you do something, you need to use different sources. When I do my debates, usually I try to find more sources that I can, and usually I also use creationist once, just to be as fair as possible. Of course, everyone has a bias, but you need to try to overcome that kind of things, because bias is not a good thing when you are discussing science, in any case.
Diabetes of Eastern Grand Canyon. We could go through each one of these. I probably won't try and drill into one of them due to time constraints here. But the point is that just like all other dating methods, there are anomalies found all over the world. This is at Somerset Dam in the Moffat intrusion in Australia, Kungara, Australia, Mount Garuho, I believe that's pronounced, in New Zealand, and so on and so forth. So isochrons don't really provide any better reliability for dating than any other method that's out there. And so on the closing notes of primordial elements, you can kind of see the problem here. Isotopes in the secular paradigm, for any elements heavier than lithium, they're supposed during supernova explosions. But the problem is, it's a random explosion and you don't know what ratios you're getting any isotopes in. If this even worked, it's purely...
Yes, but it's not like we are looking at isotopes at random. We are looking it in certain conditions. So condition that where you know that you will not find any contamination. Some kind of crystal, for example. You know how crystals are formed, and usually you know in some cases with rocks and things like that, that gases and things like that does escape from lava. So you will get a closed system at the end of the rock formation, and from that you will start to get the ratios. It's why we know that those are accurate. It's not like it's a random thing.
Hypothetical, actually. It's not even theoretical, it's purely hypothetical. If this even worked to produce heavy elements like rubidium and strontium, how do you know what ratios you're going to start out with? You're almost certainly going to get a broad spectrum. The fact that it's a molten liquid in the core, and the secular paradigm requires billions of years that the Earth has been here, which basically means that the...
Fun fact, to cool down the surface of the Earth, even without nuclear decay, we will need hundreds of millions of years. And to say that was Lord Kelvin himself, and every creationist is quoting his laws, the laws of thermodynamics. But when we are talking about him, telling everyone that the Earth is at least, I think, 500 year 500 million years old. Yeah, they forgot about that.
The mantle for otherwise solid material when it's cool inside the Earth for billions of years. How can it not be anything but a mixing line like this? And so the fact that you do find non-isochron plots is actually perhaps could be construed that the Earth really isn't that old and that this mantle material has not been mixing that long. So with that, I wanted to bring out one really super important point about isochrons. And that is, what if you found the perfect isochron? Here's the kicker. The perfect isochron, to me, basically implies that the ratio of the parent and the daughter is exactly perfect in every and equal in every single sample that you take. So, for example, if you
That will be simply impossible. It's impossible to be completely perfect in anything you do in science. You will always have a margin of error, because even if anything is perfect, your your lab will not be perfect. You will always have a little bit of contamination of some sort. So yeah, it will be impossible.
let's say it's rubidium 87, strontium 86 on the y-axis here. If every single sample, let's say you pull one sample and it had, and I'm just throwing numbers out here, but let's say it had 3 rubidium atoms and 4 strontium atoms, and then you grab another sample, but you count more atoms. Let's say you got 6 and 8 that time. And then you count another sample, and let's say you got 12 and 16 in that one. And you just keep on doing it. But if you pay attention to the numbers that I rattled off, every one of them crunches down to the exact same ratio. What that means is, and if that were true on the y-axis with the daughter and its variant, if you had the exact same thing happen there, what you would get is literally a single dot. That's it. You would not have a whole bunch of dots. You can have as many samples as you want, but if they all come out to the exact same ratio,
Just dream about it. It's literally impossible in a realistic setting to have something like that.
you can't get a line out of it because all you can get is a dot. Every one of them equals the exact same thing, and the ratios fall on the exact same point on the graph. So there's no line that can be drawn from a quote-unquote perfect isochron. So with that, that was kind of the highlight of the presentation, is that you can mix anything and get an isochron. If it's too perfect, all you're going to get out of it is a dot anyway. So Donnie and I am wrapped up with my part of the presentation, and we can move to Q&A.
Okay, so I can stop there with this kind of video. I was responding to the presentation of T-Rock. Of course, if Donnie wants me to respond to anything else, or if he does have something to say, I'm more than willing to respond and to interact. I love to do these things, but I want to show a little thing before I open maybe the stream. I would love to chat with someone if someone wants to open on the video, but connectivity finestra. Okay, continue. So here you can see the actual paper from creation.com, I did not find anywhere the dataset. Yeah, reference all from a creationist work, the rate project. So yeah, I would love to look a little bit more on this kind of data, but I did not find the dataset anywhere. So yeah, I think that's quite a problem, and I would love to know more, but I think that no one will ever answer. Okay, my thanks. You are working. Just think that it's 10 and a half in the evening, so it's quite late here, and I think that it's still yes, evening in your place. Uh, Maybe not even evening. So yeah. Thanks, Maya. It's an honor to have you here. So yeah, I'm not convinced at all on this kind of uh, data sets. I think that's when you are okay. Yes, basically evening, but we are quite far. How many hours? 16, 12. Yes, 6 hours. Uh, we are 6 hours apart, Maya. So yeah, those were my thought. Sorry, what I'm thinking about this kind of video from T-Rock and Standing for Truth. I will do more videos because I have another video to answer, a very short one, 8 minutes of video. I was quoted in a video from a creationist, so it's a first for me, and I want to respond that. And also, Professor McQueen cited me in one of his videos, and it's an honor to be quoted alongside someone like Erika and King Crocodile. I think I do not deserve that, actually. So it was really good for me to see my name in conjunction with those beasts. Yeah, someone has some questions I would love to answer. It was a first. It's the first time I'm in my new place. I was trying how good was the connection. I hope that everything went smoothly. Uh, so it was a first. It was quite hard for me to experiment with a couple of things with StreamYard and things like that. So, okay, good. I did find a good spot for the connection. I was kind of the point for taking this place, actually. So, yes, I'm glad that the connection is holding pretty well. And on my content, someone has a question. I know that there are 3 people watching, and that's a lot for me. Free all people. A lot. And also, if someone want to open, I will just provide a link if someone want to chat. Okay, I think that no one has questions. If someone does have questions, can write in the comments. I will answer, and I will be very glad to do so. I bid you farewell. Goodbye. It was a pleasure to be here. I love to do this kind of videos. I'm a newbie at it, but I hope to get better over time. So it was a very, very nice evening in your company, and I hope to see you all soon. Maya, really, you are too nice to be in this planet. See you soon. Have fun. It was good to see you too, Maya. Maybe one day we will see each other, maybe in real life. Why not? I would love to make a trip to the States. See you.